Hello, I'm Brandon Chan, and this is my Lab 4 DC and RC Circuits lab. An introduction to this lab is to predict the behavior of circuits containing resistors in a series and parallel, using multimeters to measure the actual values of conventional currents and potential differences, to examine behavior of resistors and capacitors, and some physics principles I used are energy conservation, current conservation, node rule, steady state, and series versus parallel. So for part 1, I had to make predictions, and I predicted it to be 0.02 amps, and it ended up being 0.02 amps. And for the backwards ammeter, it was just negative 0.02 amps. For part 4, I ended up with 0 amps. This is because the voltmeter has a high resistance, and the current is so small it can't be read. And the voltmeter read 3 volts since there is no current, so only the charge of the batteries is considered. For part 5, we had to find the potential differences with a closed circuit. From B to A, I got 3 volts. From D to C, I got negative 0.959 volts. From F to E, I got negative 0.2041 volts. And for the rest of them, I got 0 volts. For part 6, the round trip potential difference I found was 0 volts. And for part 9, why doesn't the ammeter change when attached to the voltmeter? And this is because the resistance is too high to make a difference. For part 10, the voltmeter across the 100 ohm resistor I got as 0.02 amps. And the parallel circuit with 100 ohm resistor I got 0.06 amps. And the ammeter decreases the total resistance, which increases the current. For part 12, we had to find the resistance, which is just the potential difference over the current. And for the 47 ohm resistor, I got 47.95 ohms. For the 100 ohm resistor, I got 102.05 ohms. And the wire and ammeter had 0 ohm resistances. For the observations on the RC circuit, I found that for the battery connected to the bulb and capacitor in series, the bulb dims and the current decreases as the capacitor charges, and the bulb goes off when it's fully charged. And when it's connected directly, the bulb dims and the current decreases as the capacitor discharges, and it goes off when fully discharged. The charge and discharge times for the 10 ohm and 20 ohm bulb were 10 seconds and 20 seconds respectively. This is my graph for the time-dependent voltage across discharging capacitor. From the graph, I calculated RC from the slope, which I found to be about 6 seconds, and then my predicted RC is also 6 seconds. For concluding question 1, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? Well, a real ammeter has a resistance and therefore would have a potential difference between the two ends of the ammeter, which affects the overall potential differences in currents. The virtual one was perfect and had no resistance. And for concluding question 2, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge? Would this prediction happen in real life? Explain. In the ideal model, the capacitor charges instantly without a resistor. In real life, there's a small resistance in batteries and wires, and therefore it would charge a little bit slower than in the model. This is because the model assumes that the net electric field and resistance in the battery. This is because the model assumes that the electric field and resistance in the battery and wires are negligible. That's it from my lab. Thank you for listening.